Hi everyone, so here we're going to be talking about logistic regression. Before we talked about linear regression, where we were able to use numerical independent variables to make the equation of a line in multiple dimensions. And it looked like this, right? And linear regression, again, if we had some kind of scatter plot, trend of variables, we could make a line of best fit through them. And the equation of that line is given by whatever this turns out to be. So the idea with logistic regression is what we want to do is we want to predict a binary response variable. All right, meaning a dependent variable that's yes, no. Do you approve them for the loan? Yes or no. Are they guilty? Yes or no. You know, any kind of thing that has a binary outcome. We want to predict using these numerical predictors. Again, these are numerical. That's important. So one way we can do this is do it in terms of probabilities, meaning we'll calculate a probability, right? And remember, probabilities are always between 0 and 1. So like the probability that it's going to be yes is going to be some number. The probability that it's going to be no is, well, 1 minus that number, right? So the way it works is we're going to use a model to predict these probabilities, and then whichever one of these two is higher, that's the one we go with. And as long as a probability doesn't happen to be 0.5 perfectly, then these two numbers will always be different, and there always will be a bigger value. Okay, so the idea is we want to use numerical predictors to predict a probability. We have a way we can use numerical predictors to predict the equation of a line, right? But a line does not give values between 0 and 1 necessarily, right? I can extend this however far down I want negatively and however far up I want positively, right? So this is going to give me numbers that are less than 0 and bigger than 1. So we want to modify this. Okay, so one way we can do this is we model what's called the log odds ratio. Okay, so the idea is we're going to take the odds ratio, right? And what I mean by odds is, you know, like the ratio of yes to no probability. You know, those are the odds. So log odds would be something like the natural log of that. We're going to model the natural log of this of the odds ratio, right? This is the odds ratio, okay, by a linear model. Okay. And the idea is that this fixes the problem. This fixes the problem of only getting values. This fixes the problem of getting values outside of 0 and 1. Because what's going to happen if we work out the math, I'll call this Z. That's a bad Z. All right. we get the natural log of the odds ratio. And to undo a natural log, algebraically, you have to exponentiate both sides. So this is going to be p over 1 minus p equals e to the z, exponentiating both sides. And then solving this equation for p, here's what we get. We get, so actually notice right now, right, z could be anything, right? It was this linear model. It could be anything, any number you want, right? It could be any number you want, extending this in either direction. But when we do this e to the z, when we take this step here, the exponentiating, look what happens. Like if you look at a graph of e to the x, how that looks like is like this, right? So it has a lower bound at 0. So e to the z is, that's a bad z again, is always going to be greater than 0. So this piece has been addressed. We've been able to get that much. Now we want to get this much. And we're going to see that it works out when we go through the algebra. So if I want to solve this equation for p, I have to multiply both sides by 1 minus p. And then if I distribute that out, it's going to be e to the z, and then minus p e to the z. I'll add p e to the z to both sides. That's going to give me just e to the z here. I'll factor out a p. To solve for p, I have to divide by this piece. So at the end of all that, I get p equals e to the z over 1 plus e to the z. So let's think about this again. So e to the z will always give me a number bigger than 0. Okay? So we have that piece taken care of. Now we want to check, what we want to check is that this gives us a number. We want to check that that gives us a number between 0 and 1. All right. So we have this piece taken care of already because this is always going to be bigger than 0. And if you're taking that and then dividing it by a positive number, a positive divided by a positive is still positive, so it's still going to be bigger than 0. All right. And the next piece showing that this is less than 1 is actually pretty easy because look at what we're doing. We're taking some number, dividing it by 1 plus that same number. So take any number you can think of and then divide it by that number plus 1, right? The bottom is bigger. The bottom is bigger than your top, right? And if you're dividing by a number that's bigger than you, well, you're going to end up less than 1, right? Then you're just going to be a fraction. So we have that this is going to be a number between 0 and 1, which is what we want because it's a probability, right? P equals this. P is a probability, right? So the idea with logistic regression is we can calculate kind of like a linear model here. And whatever that model is, we're going to apply a data transformation. We're going to apply a transformation where we're going to do E and raise it to whatever that model is. This is our linear model. Divide it by 1 plus e to the z. Again, z being our linear model. And you can actually make this a little bit easier. Here we have to plug in the model in 2 places here, but with a little bit of algebra, we can see that if we do e to the z over 1 plus e to the z, which is a little bit of algebra, you can see that that's the same as 1 over 1 plus e to the minus z. And if you want to see that worked out, we can, but it's not too terrible. So here, looking at this version of it, you only have to put the linear model in one place. All right. So you have a linear model, and then you put it through this little transformation here, and that gives you outputs for probabilities. Right? So you take numerical inputs, you get a value, that value gets plugged into this exponent, and then you do all these calculations, and then you get your probability. And that's how this is going to be played. And most platforms that have logistic regression already kind of have this transformation done for you, right? It knows that you're doing a logistic regression, and it does all this math for you to calculate the probabilities. And we're going to see some of that in SAS when we get to it. So again, the idea is we start with a linear model. Plus on out through beta n xn. All right. But we want to use this to predict something that's between 0 and 1, a probability. And when we apply this data transformation, this always gives us a number between 0 and 1. So this is a valid way we can use a linear model to predict a probability. And that's the game that we're going to play here soon in SAS. So that's the kind of the mathematical foundation of it. So you go through calculating the parameters and then plugging it into this function, this transformation here, which will give you all of your probabilities. And then you'll have, for each observation, you'll have a probability. You'll have 1 minus that probability also. And then whichever one of these is bigger, that's the classification you go with. All right. And we'll see more of those examples in SAS. For now, we'll leave it here with the mathematical foundation for you to sit on and go through a couple times, and please let me know if you have any questions on this.